Sairam everyone. So in the previous couple of sessions, we are discussing about this Mos capacitor, right? Mos capacitor. So this Mos capacitor is basically the heart of Mosfet, the device we're going to learn today. So let me first briefly give some so we'll first see this MOSFET basically they are fall in this field effect transistor categories, right? So if you see in this field effect transistors, or in short we call it as FET, right? FET. So they are basically classified into two different types, right? So one we know we already studied in our previous course, that is JFET, this junction field effect transistor, and another type which we are learning now is called MOSFET, right? That is metal oxide semiconductor field effect transistor, right? And JFET we have studied that there are two different types. So if the channel is N type semiconductor, then we call that N channel JFET, and then we have other P channel JFET, right? And the MOSFET basically broadly there are two different types. So one is called depletion type, and other one is enhancement type. So we'll discuss much detailed about these two types, depletion and enhancement type. Okay, before getting into these two types, let me just compare the working of a MOSFET and BJT, that is bipolar junction transistor, right, which we just learned a few weeks ago, right? So if you compare them, so let me just draw a table. So we are comparing BJT. So BJT is here, bipolar junction transistor, and then we have MOSFET, right? So we'll see that what are the advantages and disadvantages of going MOSFET by comparing this table. Okay, so we are comparing here, comparison. So if you think about the types, so we already know that BJT there are basically two types. It could be PNP or NPN, right? In case of a MOSFET we just discussed, so there are basically two different types. One is depletion, and in the depletion the channel could be N or P. Okay, so let me write in cap letter. So N or P type channel, or we'll stick to the small letter. Okay. And then we have another type is called enhancement, right? So this also could be N or P channel. Okay, and then if you think about the output control, in the BJT we control by the current, right? Basically the base current, right? So it's a current control device, BJT, current control device, and that is the current, basically the base current we control, right? The IB. And in case of MOSFET, it is a voltage control device. Okay, so we'll see that control device, and here we basically control the gate voltage. Okay, so we'll come to the device structure, then we'll understand even better. And then coming to the input impedance, which is very important for a device, right? So for a BJT, the input impedance is quite low. For a transistor, it is very high, because in the input we have a oxide layer which is highly resistive, so our input impedance is very high. And then if you see the frequency response, the transistor frequency response comparative to the MOSFET, again these are all comparative, right? So this is low, and for MOSFET it can be very high. And then the application, why do we use them? So application wise, we use transistor especially for low current application, right? So typically few milliamperes, sometimes can go to just a couple of amperes, not more than that. But for MOSFET, it can be used for very high power application, like high voltage and high current, both MOSFET can be used. So you got a brief comparison between this BJT and MOSFET, and you can see that MOSFET has several good advantages, better than BJT, like handling high, it has got high impedance, high frequency response, so it can operate very high frequency, and then it can handle very high power as well, right? And if you see the power consumption wise, the MOSFET power consumption is much lesser than BJT, bipolar junction transistor. Okay. Now we'll move to a very basic MOSFET structure. Okay. So as we already just said that MOSFET can be of two different types, depletion type and enhancement type. So I'll just tell briefly. So in depletion type, the channel, okay, so better we'll first see how the MOS structure looks like, a typical MOSFET structure device, how do they look like, and then we'll come back to this difference between these two. Okay, so a typical MOSFET generally starts with the substrate. Okay, so we first take, it's made on a substrate. So we take, let's say it's a substrate, it's a p-type semiconductor, and this starting is, we call it as substrate, and on the top of the substrate we build the different components. Okay, so on top of the MOSFET, we have two heavily doped opposite doped region. Like this is a p-type substrate, so we dope to heavily doped region here on the MOSFET. So this is N plus, and this is also N plus, right? So these are basically, one is source, other one is gate, and on top of that we have the oxide layer, the insulating oxide layer we have on top of it. So let me just take a different color. So we have the oxide layer, and now let me just draw the metal contacts. So this N plus, this is the left side, let's say this is the source. So we have metal contacts here, and then this is our drain. So we have another metal contacts. So this metal contacts, it's basically all the way, and it's touching the semiconductor, right? So there is no oxide layer in between, because oxide is insulator, right? And here we have our gate. So gate electrode is put on top of the oxide layer. It is not directly on top of the substrate. You can see in between we have the oxide. So this region this we have oxide. Okay, so that's why the gate and substrate resistance is very high, right? That's what the input resistance we call, it's very high. Okay, so let me just name these terminals, and we also put electrode on the base, that is on the substrate. So here on the bottom also we have a large electrode. So this electrode, this is also known as, let me use the white color here. This is known as body, or we simply denote this terminal as B. Okay, so this is the body of the MOSFET, right? It is directly connected to the substrate. And now the other three terminals, so let me just define. So we have here our source, then we have a gate, and we have a drain here, right? Now in this diagram, as you can see that we have taken a p-type substrate, and we basically create this N plus region by again ion implantation, right? So obviously they create a p-n junction, so we'll have a depletion region around this interface, right? So we have the depletion region. So this is denoted by the depletion region. Like p-n junction diode, we have the depletion layer. So this is the depletion layer, and this depletion layer is width is more towards the p-type substrate, because p-type substrate is lightly doped and N plus is very heavily doped. So the depletion layer width inside the N plus layer will be very negligible, and very less, so we can neglect that width. So we are just drawing the depletion layer only within the p-type substrate. Okay, now in this condition, you can see that there is no between the source and the drain there is no channel in the sense. So N plus, then we have here the semiconductor is p-type, right, and N plus, right? So if you connect a voltage between source and the drain, the current won't flow, right? Because there is no similar carriers, right? So here we have plenty number of electrons, here majority is holes, and here electrons, right? And if you connect just simply source and drain, there will not be any current flow, right? And this type of MOSFET, when it is not connected, right, to any potential, and there is no formation of any channel, so this kind of MOSFET we call it as enhancement type MOSFET. So enhancement type MOSFET, there is no channel. So we'll get to that more on this concept of channel later. Okay, so there is no path basically which can connect this source to the drain, right? Because these electrons cannot simply go and reach the drain. Right now, if we supply some gate voltage here, so let me just first tell. So this type is called enhancement type. Enhancement type MOSFET. So in normal condition, the resistance between the source and drain is huge, right? So they are basically open. So this type we call it as the source and drain. This terminal, they are open, right? It's an open condition. Like in relay, we call it, right? So this kind of MOSFET is normally open. So if you don't apply any bias in the gate, there will not be any current flow between source and drain. So that's why it's called normally open device. But whereas the other type of MOSFET, if you, I'll just copy this one. Oops. Oops. So in the other type of MOSFET, what we do is while creating the MOSFET, um, so the other type of MOSFET where actually we impinge or we implant actually some ions so that we make this in between the source and drain region. Also we make it N type. We make a channel basically. So instead of so I'll just draw this once. So you dope it such a way that the N type and now this is the depletion region. So this whole region, I'll just said it once. So this whole region is now N type, even when we are not biasing this MOSFET. Okay. So at normal condition, there is a channel already between source and the drain. So this is actually we made it purposely while making this device. So we also impinge those or we implant the ions under the gate also, so that we have a continuous channel from source to drain. So in this condition, if you supply some voltage across source and drain, obviously you can see that this is an N-type channel full, so it has got electrons all over, so easily the current can flow between source and drain, right? So this kind of MOSFET is called depletion type MOSFET. Depletion type MOSFET, and here we already have the channel. Okay, and here the source and drain, they are in closed condition. Closed condition in the sense already channel is there, right? So the current can flow even without any gate voltage, right? So this is normally close, right? Normally close. Like in relay, if you remember, there are two types of terminals, right? So if you take a relay, let's say it is a single pole double throw relay SPDT. So usually you will have three terminals in the relay, right? So one is common, and then so this is common port in the center, and then we'll have NO and NC, right? So one terminal is normally open. So if you use this terminal when the relay is not triggered between common and NO, the resistance is very high. They are not connected. But common and NC, it will be connected. And if you energize the relay, it goes, when the connection becomes opposite, right? So similar way, the MOSFETs are also, there are two types. So you can buy or you can use basically MOSFET as relay or switch, right? So that's why which type you want to buy, you want to get. So normally you can have a normally open switch or normally closed switch. Closed switch in the sense it is always on without any gate voltage, and this will be always off without any gate voltage, right? So Now we'll first focus on this enhancement type MOSFET. Okay. So in this type of MOSFET, as you can see that there is no channel between the source and the drain. So the device will not conduct any current between source and drain without any gate voltage, right? So let's go ahead and see that how this kind of enhancement type MOSFET works. Okay. Uh, okay. So let me just draw a. Let me take a new page here. So we are enhancement type MOSFET. Right. So I'll just draw a very simple diagram. Maybe it is already there. Okay, so it is already there. I'll just use this diagram. Right. So as you can see here, that this MOSFET, this is enhancement type MOSFET, right? There is no channel. Now let's bias this MOSFET and see what can happen. Just remove this. So usually in the MOSFET, what we do is we generally connect the source terminal and the body, we generally sort it together. Okay. So we just connect this to terminal internally, and then if we apply a voltage between the source and the gate, so this is our source terminal, right? And this is our gate terminal, and this is drain, right? Now, it's a p-type substrate, so we want to create basically a n channel here, right? Then only the source and drain will be connected, right? So to make a n channel, we know from the Mos structure, right? Sorry, yeah, the Mos capacitor, we understood that if we keep applying a positive voltage in the gate, so the gate will become positive, and it will create a capacitor right here, the Mos capacitor. So the gate will become positive, charge will accumulate on the gate, and the negative charge will start accumulate in this semiconductor, this interface, right? So essentially what happens is, so let me just bias it once. So we are applying a positive voltage to the gate terminal, right? So this voltage is our V gate to source, so VGS, right? So at this condition, so our gate terminal here will have the positive charges, and here a negative charge will induce. So basically what happens is, here we have, it's a p-type substrate, so we have plenty number of holes all around, right? So in this holes will recombine, or you can imagine the holes will be repelled from this region, right? From nearby this gate region, right? This from this interface. So you can see that this region will become less p-type as we keep increasing this VGS, and if you keep increasing the VGS amount, after some time the inversion happens, right? So this region of the semiconductor will slowly become n-type, right? Here there will be all negative charges, or the electrons. So at that condition, if you draw this diagram, so what is that voltage called? VGS. When this VGS, we are keep on increasing it, right? And when this VGS crosses the threshold voltage, right? At threshold voltage, basically this P region, P-type substrate, it become N-type, right? So that is the threshold voltage. And if we cross this, then we'll have a N-type semiconductor here, right? So we can draw this again. We'll just modify this. So at this time, I mean, when the voltage is this VGS is greater than VT, threshold voltage. So that time we have a N type semiconductor here, right? So you can see that this here we have a now channel, right? And obviously this depletion boundaries also will change, right? Now you can see that we have a channel between source and drain, right? So let me just draw this biasing once here. So this is our source, this is gate, and this is drain, and we are applying a positive voltage between the source and gate, positive towards the gate, right? The gate terminal. So this is VGS, and now if we apply another positive voltage into the drain, then what will happen? So this voltage is VDS, drain to source voltage. So we are applying another potential in the drain. Now you can see that if you apply a potential in the drain, so easily now the electron can move into this channel, right? Because we have plenty number of electrons. So the current flow is this direction. So electron will flow from source to drain, right? Because negative terminal is in the source. So these electrons will start flow from here through this channel to the drain, right? Now, for a very low VDS, if you draw the IV characteristics of this device, then it will look like something like this. So we are basically increasing VDS, and we are measuring the drain current ID. Okay. And the condition when this VGS, the voltage between gate and source, if VGS is less than VT, inversion voltage less than the threshold voltage, then this current will be very low, right? It will be very low, almost like zero, right? Because there is no channel. Now as we cross this threshold voltage, then this channel will open up, right? And then electron can easily flow, and this will behave like a resistor or a resistance for low value of VDS. And so this is the current for VGS1 greater than V2, and if you keep increasing this VGS value, let's say you are going for VGS2, little higher voltage, so we are applying now higher higher gate voltage. So if you apply high gate voltage, then what happens is this channel width will increase, right? So this resistance of this channel will decrease. So obviously the current ID will increase, right? So this is for VGS2 greater than VGS1. So we're applying higher voltage in the gate. So now channel width is more. So if the channel width is more, mean we have more number of electrons in this case, in this region. So obviously the conductivity will increase, the current will increase. But if you see carefully, now if you keep increasing this VDS value, will this increase like linearly? It will not increase. So let's see that what will happen if you keep increasing this VDS value, right? So if you see this carefully, that VDS, we're applying a positive voltage, right, in this in the drain, right? Now if we keep increasing this VDS value, and if this voltage, And if you see the voltage between the gate and the drain, gate and drain, so if this VDS keep increasing, then after some time what will happen, this drain voltage will be much higher than the gate voltage, right? So if you consider now this region, so in this region the N plus will get comparatively positive voltage than near this gate, this region, right? So this channel, whatever it was open now, this will slowly get closed, or the channel width will decrease, right? So so let me draw a fresh diagram for that scenario. Okay, so we'll take one more MOSFET here. I can take the same one. So just modify this again. So earlier the channel was opened. Now as we keep increasing the drain voltage, I mean source to drain voltage, then what happens is the channel will slowly close off, or we call it as pinch off. This channel will get pinched off, right? So if you draw the full device, this diagram, they are sorted, and then we are applying a constant voltage between so this is our source, gate and drain. So we have created a channel by applying a VGS. So VGS is greater than the threshold voltage, but what we are doing is we are applying a positive voltage in the drain, right? So as soon as the voltage, this VDS, so this is the VDS, this is okay, this I wrote already. Now if this VDS value, or this voltage between drain and source, if it reaches the value of VGS minus VT, the difference between the gate voltage and the threshold voltage, then the channel get pinched off. Pinched off condition happens. So if this channel get pinched off, then the current ID, which was increasing as we are increasing this VDS, the voltage between the drain and source, like here, it was keep on increasing. But if after some time, as the channel width is decreasing, so this current will not increase linearly, it will start decrease. I mean, it will not follow this linear trend, the slope will change, and after some time, when we reach this condition, this VDS equal to VGS minus VT, the current, or the drain current, will saturate. So the IV characteristics, if you draw complete IV, so here we just draw IV characteristics for a very low value of VDS. Okay. Now in practice, when we keep increasing the drain voltage, I mean VDS, we'll see the IV characteristics. Okay. So here, so in the x-axis we have VDS, this voltage between drain to source, and then in the x-axis we have the drain current. So usually this VDS, the order is in volt, and ID usually we get it in milliamperes. Typical values in milliamps. Okay. So now we'll draw it for different values of VGS, that is get to source voltage, right? Now, so what happens when you increase the gate voltage? Again, once again, I'll recap. So when the gate terminal, there is no voltage, there is no channel, right? So the current between the drain current will be very less. Now, as you keep increasing this VGS, when you cross this threshold voltage, the channel forms and the current start flowing, right? The drain current keeps increasing, but for a constant VGS, if it is even if it is greater than the threshold voltage, if you keep increasing VDS, this pinch off or this channel width gets reduced. This pinch off condition happens, and at the end the current gets saturated. So let me just draw the IV characteristics and explain once again. So we are drawing it for different this get to source voltage VGS. Okay, so when VGS equals to 0 to start with, VGS is 0, or if it is less than VT, right, that is less than threshold voltage, that inversion didn't happen or the channel didn't form, this channel bit below the gate, it didn't form. So at that condition, this current value, the ID will be very, very less. It will be of the order of maybe some nanoamperes to picoamperes, very less, very less. The order will be some nanoamperes or picoamperes, because you can see only insulator, sorry, there is no channel, so they are isolated, this N plus and get and sorry, the source and drains are isolated, and there is very minimum number of electrons present for this substrate, right? Only those electrons will present, that is minority carriers, right? So the current will be very less. Now as we increase the value of VGS and it crosses the value of the threshold voltage, sorry, when this crosses the threshold voltage, so this curve is for less than threshold voltage. Better write it clearly. So this curve when VGS is less than VT, right? Now it is greater than VT, that is threshold voltage, so inversion happened. So at that condition, initially the current rises linearly for lower VDS, but as soon as the pinch of voltage or this pinch condition comes, so at that condition the drain current saturates and flows like this, right? Now I'll just draw a guideline. Now, if you increase the value of VGS, that is higher grade voltage, so channel width is now little more. So the resistance has decreased between source and drain because channel width is more now. If you increase the gate voltage, this depletion width will increase, right? So, and at that condition, this VGS is more, right? So the pinch of condition, this is the pinch of condition. So we obviously need now more VDS value. So the saturation will happen little higher value of VDS. Okay, so actually they all merge to this origin. So here we have VGS. Let's say this is for 4 volts, this is for 5 volts, this is 6 volts, this is for 8 volts, and so on. And you can see that this point from where it saturates, right? This the ID or the drain current saturates. So this point is basically the pinch off happens, right? So this is where the ID saturates, and this voltage is known as VDS, that is voltage between drain and source, right? It saturates, so VD sat, where it meets the condition, that is VGS, voltage between drain and source, and gate and source minus threshold voltage, right? So at this point, because every point we are changing this VGS, so obviously VDS will increase, right? And yeah, and VDS value typically it is around like 10 volts, 20 volts, 30 volts, 40 volts, 50 volts, and so on. And similarly, the current, it will be in milliamps, so maybe here it is just 10, 20, 30, 40 milliamps. Okay. So this is the IV characteristics for this. But again, one more thing is this current, it will not be exactly saturate like we studied in transistor, right? There is an early effect, and this current will not be exactly parallel to the x-axis. It rises slightly. There is a slight dependence on the this VDS or voltage between the drain and source. Slight dependency is there, but we take it as a saturation current. Okay. Now in this condition, if you see the mathematically how this current relates, so let me just tell you that formula, and before that this this width W, or the depletion width, the channel width, this W is proportional to VGS minus VT, that voltage, right? So it's proportional to the source to gate voltage, and this length is called L. This gate length, this is L, and if you consider this W is as depletion layer width, and this is L, of course. So for a higher VDS, this width is not constant, but for a typical value, very low value of VDS, this channel width will be almost constant throughout the channel, throughout this gate region. Okay, so that is W. And yeah, now this ID depends on basically few parameters. So we'll just see that ID is the drain current, right? So the drain current, the ID, which depends on for we are doing now here a p-type substrate, and this is the N channel, right? This is a N channel enhancement type MOSFET, right? This is the N channel MOSFET. So for N channel, the substrate is P. Okay, we are creating a channel N, the inversion layer is N type, and source and drain, they are also N type, right? So this drain current, it directly relates with W into mu N. I'll come to that. W mu N, then COX, that is the capacitance of this oxide layer. Oxide layer is here, this region is the oxide, right? So it could be silicon oxide or could be any dielectric material, by 2L. So L is this length between source and the drain, distance between the source and drain, and twice VGS minus VT into VDS minus VDS square. So the drain current, it follows this relation. You can see that qualitatively we'll understand this. We're not going to derive this formula here. So you can guess it easily that if this width is more, of course, the channel width is more, so it will be less resistive, right? This channel will be less resistive because more number of carriers. So obviously the ID will increase. And if this L increases, this length, so this length means the resistance, path resistance will increase, the current will decrease. So L is here, and then it depends on the capacitance of this oxide layer here. And then within the bracket there are two terms, twice VGS minus VT, that is this voltage difference, right, where it starts the inversion, into VDS minus VDS square. Now in this formula you can so this is the drain current for any condition, right, for a given VGS and VDS, because other terms are don't change, right? We cannot change. We change basically these two parameter, VGS and VDS. So this from this relation we can calculate the drain current. This mu n is the mobility of electron, because this is the n channel, right? And electrons will be the carrier for this particular example, right? So this is the mobility of electron, right? Mobility of electron in the channel, right, here in this region, in the channel region. Now we can calculate the this saturation current, right? This ID saturated current we can calculate, or the drain saturation current, that is ID sat. We can easily calculate, because at saturation current it holds this relation. When the VDS, that is voltage between drain and source, become VGS minus VT, at that time whatever the current flows through the device or the drain, so that is called the ID sat, right? So we can easily calculate the ID saturation. Let's say this is equation number 1, and we know at saturation point this VDS at saturation condition, it becomes VGS minus VT, right? So this is equation 2. Now if you use this value of VDS equal to VGS minus VT and put the values here and here, you can easily get the drain saturation current, right? So it will be W mu n COX by twice L into, you can see that if you put this value here, VDS equal to VGS minus VT square. So here again VGS minus VT square whole square will come, here also whole square will come. So only one term will survive, right, which is VGS minus VT whole square, right. And just take same bracket. So this will give us the saturation drain saturation current, right. So you understood the IV characteristics and how this enhancement type MOSFET works. So this is a N-channel enhancement type. We can also do the similar thing for a P-channel MOSFET, right? P-channel enhancement type MOSFET. So in P-channel enhancement type MOSFET, the substrate will be of N type, and then we'll be doping here P plus and P plus for source and drain, and obviously that time we'll be supplying a negative gate bias voltage to invert this region, right? Now if you see the now let's see the circuit symbol for this MOSFET. Okay, so the symbol, like transistor we draw, right, for this kind of diagram, right? So we have their collector, emitter, and base, and if you put this arrow from base to the emitter, so it defines as NPN, right? So this is our NPN transistor, and base emitter, and if the arrow is other way, so it is called PNP. And if you notice carefully that at the arrow we always put from P to N, right? And it also defines, it also says that this arrow direction, I mean for easy remembrance, that this arrow direction, it tells about the flow of current if that junction is forward bias. Okay, if you reverse bias, of course it will be other way, but flow of current in forward bias. Okay, now we'll see for this MOSFET. Okay, so MOSFET, as you can see here, we have different terminals, right? So we have source, gate, drain, and body, right? And in normal operation, most of the time we sort the source and the body with a wire, right? They are usually sorted. So the circuit symbol, I'll just draw it. So we'll first draw it for the same one. It is N channel enhancement type. Enhancement type MOSFET. So we're doing circuit symbol. So we'll first draw the different terminals. So this is our gate, and then we have a drain, we have source, drain, this is source, and we have body or the substrate B. Okay, now when you draw like this, so where will be the arrow sign, right? So we generally draw the arrow from P to N, right? So in this enhancement, N channel MOSFET, if you see, the body is P type and the gate, this will become N type, right? When we bias it. So this will become N type. Body is P, gate is N. So obviously the arrow direction is P to N this way, right? And one simplified way we sometimes draw it, because because this body and source is, they are connected, so we can also draw like this. So this is our gate, this is drain, and this is body, this is source. So we can connect this together. And this will be just the source. So we don't put the ground terminal, and the arrow is, arrow is inside. Now even simplified circuit, even simplified diagram, we write it like in this case it is enhancement type MOSFET, right? So it is a N channel enhancement type, because you can see that in normal condition the source and drain, you can see there is a gap, right? Channel is open, right? There is a gap. But the other type, the depletion type, source and drain, it will be connected at normal condition, right? So they will be joined together, right? So in general, for a N channel MOSFET, we draw it like this, very general. It's an N type MOSFET, N channel MOSFET, that's all. So at that condition, we draw it like this. So we have a drain, we have the source here, and the current basically from source it enters, right? As you can see here, this is a positive. Sorry, the source is in sorry, it will be outside, right? It will be outward, because from the source terminal the current enters from the source, and the direction will be other way. It's like this. Sorry, we put the arrow on the other half, the arrow here. So if you draw like this, it says it is the N channel, because for the N channel the source will be of source is here, right? Yeah. So this is how we denote the current flow direction. If you see in active mode operation, the current flows from drain to the source. Usually we bias it source as negative. This will be positive, positive, right? So the current flows from drain to the source. And in case of a P channel device, so the P channel, so this is for N channel. Okay, we wrote already on the top. P channel enhancement type MOSFET. So we have the gate, drain, body, source. Sorry. So this is the body, this is gate, this is our drain terminal, this is the source terminal. And simplified way, it's very similar. Sorry, so for again doing mistake here, right? Because for P channel, for the P channel, the body is N type and gate will be P type, right? So body is N type, so the arrow is towards the B. It's like this. Basically for P channel the substrate is N type, right? And we'll invert the gate region, so this will become P. So P to N, arrow is out this direction, opposite to the above. And we can even join this also. Typically we join this too, so this is the drain. So it's basically 3-terminal device only, drain, source and gate, right? And even most simplified one, we're not mentioning any types. So the current direction is inward in the source terminal, and we always put the arrow in the source terminal, okay? In case of MOSFET, like in transistor we put in the emitter terminal the arrow, not in collector. So here in MOSFET we always put the arrow in the source terminal, okay? And yeah, so this is for the enhancement type. When you draw it for depletion type, in the depletion type this drain and source, they are basically connected, right? Because already channel is there. So that time we just connect this, we draw a continuous line here, that's it. So that will be for depletion type MOSFET. Okay, so we'll stop it here, and then next class we'll discuss about depletion type MOSFET. Okay, sign off.